Hello, welcome to one more lecture on the fundamentals and biomedical application of quantum science and engineering. Last lecture we saw very nice model of the molecules, the atom and everything. Today we're going to see a tremendous important example in quantum mechanics, which is the harmonic oscillator. You know what is a harmonic oscillator, right? It's a particle it's bounded by an external force that makes it oscillate with regular frequency. So that's the harmonic oscillator. We have also non-harmonic oscillator that normally we call unharmonic oscillators, which has frequency that depends on the amplitude in general. This case, no. Doesn't matter how is the amplitude of oscillation. So particles can oscillate in different amplitudes, small amplitudes, big amplitudes, and they have the same frequency. So that's the harmonic oscillator. And why the harmonic oscillator is so important for quantum mechanics? Because, you know, almost everything that we start in equilibrium and then we displace it from an equilibrium, try to return and have those oscillations. So oscillation is present in almost everything. Nothing is so rigid that does not oscillate. Therefore, knowing how the quantum mechanics works in those oscillations is very important. Besides that point, there are also the molecules that vibrates. And the molecules that vibrates, they look like harmonic oscillators in some context, right? In some small oscillations. When you have something bounded to a surface, you know, it will oscillate. So if you have a surface like this, and you have an atom or molecule that's bound, and normally looks like this, and these things can oscillate here. And then we have a Aroma Spectroscopy. Aroma Spectroscopy is based in many things, but especially on the vibrations. Because you're going to see that, as everything in quantum mechanics, the energy of vibrations can now be quantized. So we're going to have some energy, and then we're going to have another energy. We have nothing in between. And then there are those levels of vibration that allow us to do Aroma Spectroscopy, which is a important tool in the understanding of many things in all types of engineering. So Aroma spectroscopy is very, very important, and we're going to have a special chapter for it, special lecture for spectroscopy in general, as soon as we finish all these important examples in quantum mechanics. So normally the force is proportional. If we want to see mechanically what's happened. Mechanically, it's like this. We have a particle of mass m that is bounded by a spring, and this spring has some constant k, and there is a force always opposite to the displacement. And if we look to the potential notation of it, remember, the potential is we go from the force to the energy that the work the force can do it. And of course, we are talking about a conservative force, so we can express as a potential, and the potential goes with x squared. So all the things that goes with x squared normally try to represent oscillations in many contexts. And it's half of it, because if you take the derivative with the minus sign, you get the force. And the force that this corresponds is equal to minus kx. So if you take the derivative, these two cancel, and you get a minus here, because the force is minus the derivative of the potential with respect to the coordinate. And you get this. So this is the potential we have. And because normally the harmonic oscillator is characterized by a frequency, and the frequency is the root square of the ratio between what we call the spring constant, which is this k, divided by the mass of the particle. You know, you can come here and substitute to get, you know, you see that if you take this square, the k will be omega square, which is the natural frequency of oscillation for the harmonic oscillator times the mass. So the potential actually in most part of the places is expressed in terms of the frequency of the oscillator. So the potential is like half, right? Let me use a color that everybody can see. So it's like half m omega square x square. That's the potential for the harmonic oscillator. And of course, if you look in this perspective, the harmonic oscillator is like a potential. It's like this physical system that confines the particle. And the particle will be a wave inside this, as we saw exhaustively. You know, we saw this many times, that the particle, if we put a particle here of mass m, the particle will behave like a wave in these boundary conditions, and we are interested in the states and the energy. How are the energy spectrum of this? How can a harmonic oscillator have energy? What are these energy spectrum we have? Okay, so as always, we're going to start with a Schrödinger equation, which is the equation that gives us the wave function, which represents this matter wave in this harmonic oscillator. And here we have the kinetic term, which is the minus h bar squared divided by 2m times the second derivative of the wave function psi, plus the potential that we just wrote, the potential as being half of m omega square x square times the wave function psi, and this is equal to E psi. This is the time-independent Schrödinger equation. So we are dealing with this equation because we wanted to find out the stationary states, right? Which give us the spectrum of energy. Don't worry, sooner we're going to change, and we're going to start to put potentials that depend on time. Because in many applications, especially in biomedical systems, things depending on the time. And we will solve a few problems with time independence. In special, the interaction of the energy of the electromagnetic field with the atomic system, with the electron in there. Okay, so this particle in this harmonic oscillator is also very important because we're going to see that oscillations in general of the electron in the atom, in some situations can be mimicked by a harmonic type of oscillator, because you deform the electron cloud or the electron orbital, and they can behave near the equilibrium as a harmonic oscillator. Okay, so we gotta solve this equation, and solve the equation means getting the energy. We want to know what values for energy this quantum system can allow. What are the energies we can have? And of course, we want to know the wave function, because we want to know how is the probability of the particle be distributed in this physical system, in this configuration. So that's what we want to solve. That's what we want to do in this lecture, and of course we want to do some more things in this lecture. Okay, so the starting point for us is the equation. We're going to start with this equation and try to solve it. You know, it's not an easy equation to solve, because if we didn't have this x squared here, we will know what's this equation, right? We learn what is the equation where the second derivative times plus a constant times the wave function is. We knew how to solve that problem. But here we have x squared. And that makes the things a little harder to solve. And how to solve this equation to get the spectrum? We're going to have to use some mathematical tools. There are many mathematical tools for solving equations. And, you know, you learn in special mathematical courses all those tools. And I'm going to use some, but I'm going to use something very simple. We're going to do a variable substitution, change of variable, and then we're going to use a series to solve, which is a conventional way of doing. Normally, when you're going to solve a problem like this, you look to the extremes. So you look at asymptotic behavior of the wave function, which is given by the equation. And then you combine things and you come with the solution. That's very traditional in doing. You know, the next lecture we're going to do is the solid. But then comes the atom. We're going to do the three-dimensional atom and a three-dimensional molecule because we need to understand about chemical bond and things like this. And then we're going to do a lot of those procedures to understand how is the solution and how nature allow the energy to be there, right? Because that is the energy spectrum. So from the Schrödinger equation we just wrote, we're going to multiply everything by 2m divided by h bar. And we end with this equation here. So we just modify it because normally we like to start with differential equations that has the derivative like this and with coefficients, and we like to put all the constant in some other places. Okay, so this is just the original equation that we multiply, right? We just took this term, multiply everything by 2m, divide everything by h bar square, and multiply by minus. At the end of the day, we have this, right? After doing this multiplication, which is quite easy. And this is the one we have to solve. And there is no a very easy guess for this. So we're going to start to do those techniques that I told you. And the things we're going to do is make a change of variable. Because then you're going to look more clear things, right? In atomic physics, in quantum mechanics, normally people want to get rid of the constants by defining variable with special units. So basically this is what we're going to do. You see, when you define y that way, we are redefining units for the variable, right? We're not doing anything fancy. This axis here is expressing in length, but this one is expressing something else because it's length times all this. And that's what we're going to do. And we're going to define a y variable, which is basically the x times root square of m omega divided by h bar. And of course, we're going to consistently define epsilon equal to 2 times the energy divided by h bar omega. Basically what we're doing here is try to remove those constants. This is what we're trying to do. Okay? And you see here, m omega divided by h bar square appears in here. So if we include it in the x, this whole thing will be something square, which is the y. Right? But then don't forget that we need to, well, the y is the root square. Y is the root square because we're gonna need to really have in the here an equivalent term. So you're gonna have in this x this term square, right? Because it comes 2 i's. So it's going to be m omega divided by h bar, and therefore equivalent here. We're gonna have to make this. So when you make the change we just needed to substitute, you know, in the place of the function. That function will now be dependent on y. And the equation, we just make the change of variable. You know, we can do this in many different ways. So if you want to express d psi dx, this is equal to d psi dy times dy dx. That's how we make the change of variables, right? Because now y depends on x. So if we do this change, deep psi dy is equal to deep psi d x, oh, I'm sorry, deep psi dx is equal to deep psi dy times dy dx. And then we repeat this twice. We can change this whole thing. And then we're going to have terms that are going to appear here. You can see already that when I repeat twice this, I'm going to get this guy twice, and then everything is going to work out. Finally, we work out okay, because we're going to have exactly on the place of the y or the x, I'm going to put y times the inverse of this and so on. So everything is going to work fine, okay, if you do this variable substitution. I don't have time to do in detail, but I'm sure that this is a easy procedure you can do. And then this equation transforms itself in an equation that's more like clear. This new equation is the second derivative. It's the same equation, but now expressing the y coordinate, which we know is root square of m omega divided by h bar times x. So the second derivative with respect to y plus epsilon, this epsilon gonna pass to this part, minus y square psi is equal to 0. So this is a little bit easier to treat because I don't have to carry all the constants. And one thing I can do is, when I make these balances, now I have everything is the same unit. Either, you see, the coordinate and this, let's say, normalized energy. You know that h bar omega has a value of energy, so this is a number. S is y, because the root square of m omega divided by h bar is the inverse of distance. Actually, the inverse of this is called the length of the oscillator. So everything here is like dimensional less, because we redefine the energy and we redefine the length. So they are in special unitless, no unit. Okay, now I can compare these two terms, and there are situations where I go too far that this term dominates. And there are situations where this term dominates. If y is very small, this term dominates and we know more or less what's the solution. And if this term is small compared to this, if I go far from the center of force, which means if I consider y squared much bigger than epsilon, this term dominates, right? So we're going to consider first this case, when this term dominates. When this term dominates, we get as equation, right, about this term. The second derivative of psi with y squared minus y squared psi is equal to 0. And if you do a few simplifications, which I'm not going to do here, you can show that the solution is basically an exponential of y squared divided by 2. You can verify that. So this is interesting because we need this. Remember, we're dealing with a potential that is, the particle is confined around this region, right? So this is the potential that confines the particle. Whatever is the wave function I'm getting, it has to decay in the infinite, has to go to 0 when I go far from this situation, right? And an exponential of y squared. Remember, y is proportional to x. So this goes to x squared. So exponential goes to 0 when I go far from the center of the field force center, and therefore this goes to 0. So for that situation, for far from the center, when I can say that this term is bigger than that, I have as a solution a term that I call Gaussian. Because for large distance, I go back to the x, and I have the wave function must be that way. So for large distance, the wave function psi is dominated by a Gaussian type, which is an exponential square, right? And the term that appears in here, which is very important, I went back to the original units that we start, is minus m omega divided by 2 h bar. If I have a strong oscillator, means a very large omega, this is confining the particle a lot. So if the potential is very confined, the particle will be very well localized. So we will go to zero fast when I go just a little bit beyond the walls of this harmonic oscillator. But the wave function, of course, exists, even though that's the particle classically cannot be there all the time. Okay, or can never be there. So we have what we call an asymptotic behavior for the wave function. It is a Gaussian type, and Gaussian type wave function is going to appear everywhere. And then it's nice to know type of solution that generates the Gaussian type of wave function. If I have this there, it is reasonable to suppose that the new solution is a function h of y times the Gaussian, with the constraint that this function does not blow more than the Gaussian when we go to large distance. So when we go to large distance, this must come to a finite value, or to a value that does not diverge as, or does not die out as the Gaussian. Normally, any polynomial type of function do not diverge or do as fast as the Gaussian decays. So then we are safe when we go to large y. So we suppose that the product is solution, right? And now we go back to the original equation and we substitute our new proposition of solution, which is a new function h of y times the solution that we found for large y, which is the Gaussian, right? So making this substitution, we get a new equation. Now we get an equation for y, for h, I'm sorry, in terms of y, of course. So d2h dy2 minus 2y dh dy plus epsilon minus 1 h is equal to 0. And now we have to solve this equation. We, again, can solve this equation in many different ways. But a traditional way to solve an equation like this is suppose that I have a series, a polynomial. It can be a polynomial of any order, right? And there is a parameter here, which is related to the energy. And that's very interesting because you're going to see that when I get the recurrency relation for the coefficients, for some value of epsilon, this is interrupted, right? This is interrupted, and we call a truncation of the series, and therefore we're gonna find the different values of energy that allow. Okay, so let's go for the solution. The idea here is to find what are the coefficients, because if this is a polynomial, you know, I know y, I know express y in terms of x, and if I know the coefficients, all the coefficients, I know the function. So the idea here is to determine the coefficients. So I have to find relations for the coefficients of the polynomial. Right? This is the way that we solve the polynomial, the differential equations using polynomial, using series This has a name, it's called Frobenius series type of solution. Now we're gonna take this function, put in there. When we take one derivative, of course, you can imagine, you should imagine that this is a0 plus a1y plus a2y squared plus a3y cubic and so on. That's a series, right? All the terms are here in principle. When I take the derivative, this term disappears. A0 goes away. And of course, when I take the second derivative, the second term goes away. So actually, when I take the second derivative, here the series starts in A2. Right? Because all the other terms goes to 0. Here the series is going to start in A1 because A0 goes to 0. And here I have the full series. When I substitute the derivatives here, this must be true always. So what I have is that each term of order m has a coefficient that's added by this whole thing. And this must be valid always, so those coefficients must be 0. To get the 0, to get 0 for any value of y, all the coefficients must be 0. So when I do that, I find a relation between coefficients. So I find a relation between, let's say, A0, A1, and A2. And then I find a relation between A1, A2, and 3, and so on. So, because when I take the derivative, I'm going to start to mix those coefficients. You understand, right? If I take the second derivative, A3 will be mixed with what? If I take the second derivative, here will be something times y. Right? In the first derivative it gets y squared, the second derivative y. So that one going to mix with A1 here, that I did not take derivative and everything. So I hope you're following what is the mechanism for dealing with the solution of differential equations when we use series. And then when I wrote everything up and I demanded that the coefficient for any power of y be 0, because this has to be valid for any value of y, I get a relation between the coefficients that we call recurrence relation. This relation between the coefficients is called recurrence relation. And then I find that this is not any series. It's a series where the coefficient, any coefficient, m plus 2, is related to m. So A2 is related with A0. A3 is related with A1, and so on. Basically, what's happening is, if I know A0 and A1, which must be given somehow, I can recover all the series. I get the solution. And as you can see, when I know A0, I'm going to generate the even series. So all the terms will be even. And when I know A1, when A1 is not 0, I'm going to generate the odd series. So all the terms will be odd in this series. I'm going to start with 1, 3, and then go 3, 5, and so on. So A0 is going to generate the even polynomial, or polynomial of even order, square, 0, square. So those terms will belong to the even, and then will come the 4 here. While the A1, A3, and so on will generate the odd series. Well, normally I know one of the constants that will be given by the normalization, will be given by the fact that the integral must be 1. The integral of the wave function psi will be 1. And why here we already seen that we separate the even and the odd solutions is because something that I told you already in other lectures, which is the parity. Because this potential has a defined parity, as you know, this is a even potential, right? If I replace x by minus x, nothing change. I come from here to here. So the value of the potential does not change. So I have a symmetry here. And because of this symmetry, right, as I told you before, the solutions has defined parity. They are either even or odd. They are not both even and odd at the same time, or a mixture of the terms. Now, there is one interesting thing in this recurrence relation. If this term became 0, I kill the series. If for some specific m is an integer, right? This is the index of the series. M is equal to 0, 1, 2, until infinite. If for some specific m this is 0, it turns out that from that m on, the am plus 2 is equal to 0 because this term is 0. And therefore, I stop the series at that point. Normally we call a truncation of the series. I hope this is the right word in English, truncation. So this condition here, 2m minus epsilon plus 1 equal to 0, is a very important condition. M is an integer number. And I'm seeing that, you know, for some specific, depending on the value of the energy, it could be a m where this is 0 out. And if this is 0, the series truncates, stops. So let's impose this condition. Let's impose that this is 0, which means that epsilon is equal to 2m plus 1. Remember that m is equal to what? 0, 1, 2, 3, and so on. We're going to find out, and in the place of epsilon, we put our definition that we did before, that is 2 times the energy divided by h bar omega is equal to m plus 1. And then we get the energy. We get that the possible energies are given by this. And of course, I must truncate the series somewhere, because otherwise this may be an infinite series, and an infinite series may compete with the Gaussian term, and the wave function may not be 0 there. And then I got here, you know, that depending on the values of the energy, this series will have different solutions, polynomials of different orders, and this energy is m plus half, just divided by 2 here, times h bar omega, with m equals to 0, 1, 2, 3, and so on. Of course, if m equals to 0, I generate the even series. And if m equals to 1, I generate the odd series of solutions. So but m can be anything. And this is the energy spectrum. The energy of the harmonic oscillator can only be values given by this. This is the values of the energy that works and produce solutions, distinct solutions in here. Right? So the value of the energy is an integer number that can be 0, 1, 2, 3, and so on, plus half times h bar omega. So already then I got the spectrum, the energy spectrum for the harmonic oscillator. The energy cannot be anything. It needs to be kind of semi-integer number times h bar omega. H bar omega is what we call the quantum of energy of the harmonic oscillator. If you have a particle with an energy, it has to get an extra h bar omega to go to the next level, and next, and next, and next. That's a very interesting situation, right? And this is very important because, as you can see, we have a term that here for m equals to 0, that is a term that's not 0. As I told you before, when we discussed the uncertain principle, the Heisenberg uncertain principle, we discussed that nothing that's confined can have a zero energy. If you confine in space, you must have a finite energy. That's the ground state. And this is the ground state of the harmonic oscillator. It's half of h bar omega. Everything that oscillates may have a 0-point energy. That has profound consequences on everything, as we're going to show you a little bit further as we discuss the solution. So we get in mind now, we have to keep in mind that this is the spectrum of energy of the harmonic oscillator. And we're going for the solutions, right? We must go for the solutions. And as we know, m, normally we call n, in the traditional textbooks, we call n this integer. You know, I don't know why I didn't put n in the very beginning, but yeah, that doesn't matter. You know, if m is equal to 0, 2, 4, 6, that giving an even set of solutions. So means the polynomial will be even because the Gaussian is always even, right? Now, when m is equal to 1, 3, 5, 7, this gives us the odd set of solution, and the odd and an odd function times the even give it odd, so the Gaussian does not matter. Those polynomials that we get from this series, and we have the recurrency relation, so we know everything now. If I know A1, I determine A3. If I know A0, I determine A1. If I know A0, I determine A2. I know A2, I determine A4. I know A4, I determine A6, and so on. So having the recurrency relation, I get all the coefficients of this polynomial. Okay, either even or odd order polynomial. And this is, in mathematics, that gets a very nice name. It's called Hermit Polynomials. So if you go to the textbooks or some handbook of mathematics, the solution of that equation that we saw giving origin to the Hermit polynomials. And the Hermit polynomials are very nice. And here I am representing in the potential some energies and some functions. So I'm putting different n's. I'm going to call n instead of m now, right? So normally m is called n in textbooks, integer number n. It's a natural number, 0, 1, 2, 3, and so on. So we can have different energies. So if n equals 1, we get this energy. If n equals, if n equals 0, I get this energy, which is the minimum energy possible. If I get n equals to 1, I get this energy. If n equals to 2, I get that energy, and so on. And here, where I'm plotting in the left is the wave function itself. And on the right is the probability density. So the first function, if I get only A0 times the Gaussian is a Gaussian. So I get here the Gaussian. So that's the Gaussian. Right? That's the Gaussian. If I get n equals to 1, what I get is a function that's, of course, has to be odd. So when I change it, the function changes sign. The tail is still Gaussian, but then is multiplied by a polynomial that's a constant minus x, and that gives this. If I go to n equals 2, I get again an even polynomial that's given by this, and so on. If I take the square, what I get is the probability distribution of finding the particle. I'm going to just highlight here the first state. So that's the probability distribution for the particle in the harmonic oscillator for having the ground state energy, which is half of h bar omega. If I go to the first excited state, or the state, what I get is 0 in the between. So the distribution of probability, if I'm going to find this particle oscillating here, the probability of finding the particle in the center for this state is maximum, and for this state is minimum. And so on. If you go to the next state, it's always here, goes in a tail, and depending on the energy, the exponential of the Gaussian grows, it comes down faster. We get that. So that's the density of probability, which is the spatial distribution of this particle, and looks very much like the wave. But it's not so easy to do like you do in the rigid wall, the waves. So that's a soft wall. Therefore, the accommodation of the wave must have this tail. This tail corresponds to the region where probably the particle has, when it goes out of the potential, classically, the particle could not be here, but quantically it can. You can detect the particle far from the confinement because of this Gaussian tail. And this is the density probability that we have for this situation. As I told you, the main point here, you can get the Hermit polynomial everywhere in any book you want. But you must have in mind now that the energy of the harmonic oscillator is n, an integer number, 0, 1, 2, and so on, plus half h bar omega. And n equals to 0 is the ground state. We call the ground state the lowest possible energy. And the other one we call excited states of this harmonic oscillator. And they look very nicely and distributed. If you go to n, that's very high n, many h bar omega of energy. This will have so many oscillations that you can actually almost see a continuous of probability going on, which is going to the classical limit. It's going to the classical where you can see, and actually you can see that builds up a little bit further on the edges of the harmonic oscillator. This is very interesting, and look, the number of oscillations or the numbers of bumps is the n plus 1. N plus 1 is the number of bumps in this wave function. The valleys is n, but the bumps is n plus 1. And always it decays to the large distance as a Gaussian. Gaussian is very important in this situation. Now, before I end this harmonic oscillator, which is a very interesting solution, and we're going to have to keep in mind, the 0-point energy is something important. So I told you that anything that's bounded harmonically has this. Anything that oscillates like a harmonic oscillator and is quantized has a 0-point energy, including the electromagnetic field. The electromagnetic field, as we're going to see in a few lectures from now, it's like a harmonic oscillator, but what's oscillating is not a massive particle. It's the electrical field and the magnetic field. And when we quantize that system, we're going to get a 0-point energy. So it means that when you do not have light, you still have energy. And that's the 0-point. And that's very interesting, that the vacuum must have energy there, that the 0-point energy. And normally it comes from the oscillations of everything and everything. This is very interesting. And the fact that the particles, when they are confined, they have a 0-point energy, it generates a lot of interesting things. If I tell you, you may not believe me at this point, that the superfluidity, superconductivity, and many other super properties comes from the fact that when I decrease the energy of the physical system, they go to a finite energy, which is the minimum energy of the system, and this wave function start to have special behavior because it's the most delocalized possible. So imagine that I have this system and then the wave function is so small, the energy is so small that the wave function spreads out like we saw. In that situation, each atom or each component of my system occupies the whole system. And in this situation, we can have interesting properties like superfluidity, like superconductivity. Superconductivity is very interesting because that's depending on the type of particle. You can have fermions or bosons, I know. But anyway, besides that fact that has to be taken into account here, the fact that you have zero energy, that the minimum energy of the system is not zero, has as a consequence possibilities of having those super phenomena. And that's a very important thing. Normally we combine this in what we call Bose-Einstein condensation of the system, so they must be bosons. But even when we have electron in a metal, in some type of metal, it will find a way to combine with other particle and form a boson. They call pairs, Cooper pairs. Two fermions together make a boson, and they can all having the same minimum energy, and they became superfluid. The same, they became superconductor, I'm sorry. The same when you have atoms like helium atoms, helium-4 atoms, and you cool down, suddenly, instead of becoming viscous, they became superfluid. They became superfluid. And the superfluidity is a consequence of the fact that a majority of the atoms, or a large number, a macroscopic number, comes to have the minimum possible energy. If that energy was zero, that wouldn't be possible. But because it's not zero, that's possible. And you see many consequences that we see in the macroscopic world. We see by eyes a superconductor or a superfluid. We see by eyes. You can go to the internet and Google effects, visualization of superfluidity. You're going to see interesting effect of a superfluid. And that's consequence of having a zero energy. And there are many, many other consequences of having zero energy that we may mention as we come to the applications in the coming future. Well, harmonic oscillator. Things that oscillate harmonically, they have the energy quantized and they have a 0-point energy. And the quantum of energy is h bar omega. You cannot forget that. The quantum of energy is h bar omega. This is a magic quantity that is in the harmonic oscillator. So when you have a molecule and it is vibrating, is in some vibrational state, you can only go to the next giving h bar omega for this molecule. Then you go to the next vibrational state and so on. Okay, enough for this lecture, and I hope to see you in the next lecture where we're going to see the quantum solids, right? What happens when particles try to move in a periodic potential? What kind of consequences we have? See you then. Bye-bye.